So welcome back. This is the third class of review sessions, and the plan for today is to cover what I call chapters 5 and the first half of chapter 7. I'm skipping chapter 6, and we'll do that next time. So what is in these chapters? Well, having changed chalk, I forgot to get the new chalk. Give me 1 second. This is the bad stuff. We all know what happens to that. Good. Okay, so basically the plan of attack is that chapter 5 is looking at continuity and differentiability. So these are two properties that functions can have. In fact, you might even say they're properties that functions can enjoy. I don't know if functions actually have the sentient ability to enjoy it, but if they did, they would enjoy being continuous and differentiable because it's nice. This is nice. Anyway, so we have to look at what those concepts are and some simple consequences of them. And then I will do after that, skip to section 7.1, which is trig limits. If I have time, I will go ahead with chapter 6, not with 7.2. 7.2 is the other half of chapter 7. That's on trig derivatives. So I'm going to cover these two, and then if I have time, I'll start on chapter 6, which is how to solve problems involving differentiation. That's the product rule, the chain rule, quotient rule, all that sort of stuff. But in any case, let's see how we go with this. So before I start, does anyone here have any questions? Remember, we'll do the homework questions at 9:30 at the conclusion of the more formal presentation, but if you have anything on your mind, this is a good time to ask as well. Yes? How would you differentiate a modulus function? So absolute value function. Actually, can you... Sure. This is actually on my agenda in chapter 5, so if you give me a half hour or so, I promise I'll answer it. Okay? So, following along in section 5.1 of the book, this word continuous, I want to say that a function is continuous. And I got to say where it's continuous. So continuity is... The first thing I'd like to do is take a function, and let's just look at one point on the x-axis, a. And I just want the function to be continuous at a. What does that mean? How do I define it? Well, the intuition is that a little bit to the left of a, I start drawing the function. I don't have to go all the way back here. I can just start very close to a. And I want to be able to go through a and stop a little bit to the right of a. It doesn't have to be very much at all. But I want to be able to do it without lifting my pen off the paper, or in my case, the chalk off the blackboard. So I don't want any asymptotes. I don't want any jumps. I just want something to be smooth in the sense of I want it to be at least in one piece. Now, it doesn't have to be as smooth as all that. We'll look at that in a few seconds. But I at least want it to be connected somehow. So how am I going to define it? Well, what this means is when I come to x equals a from the left, I want the function to approach the height that it is at a. And the same from the right. So basically, a function f is continuous, and I'm going to write this as CTS to save time. That means continuous at x equals a, or just at a, if the limit as x goes to a of f of x equals f of a. That's the whole definition, but it does beg three sort of comments that, or really it's one comment, but it has three parts. When I write down an equation like this, what I really mean is, to be more sort of pedantic about it, I really mean, first of all, the limit has to exist. Right? We've seen last time that the limit doesn't always exist. Two-sided limits don't exist. Even one-sided limits don't exist all the time. But sometimes they do. F of a has to be defined Okay, so, A doesn't necessarily have to be in the domain of F, but I am saying, yes, it has to be defined. And finally, these two are equal, which is just the equation I have above. So, why do I say that's being pedantic? Well, I guess, if you just look at this, there's an equation. It says two things are equal. For the two things to be equal, they kind of both have to exist, right? But, I guess the limit could be infinity, and f of a might be undefined, so you might think it might be infinity. Well, that's not allowed. These things have to exist and be finite. I should really say that. I should really say that it has to be finite. Okay, so that's what it means to be continuous. Now, here's a question. Why wouldn't a function be continuous? Well, I just want to show you a few little diagrams that indicate some things that can go wrong. So here are four possibilities. Okay, check out that picture. That's just the graph of f. Is that continuous at a? No. F of a is defined, but the limit doesn't actually exist. The left-hand limit is different from the right-hand limit, and so the two-sided limit doesn't exist, and the function cannot be continuous at a. Okay, what about this one? Well, in that picture, the two-sided limit does exist, and it is whatever this height is, L. But f of a isn't defined. There's an open circle there, so it can't possibly be continuous there. Okay, how about this one? Well, now the two-sided limit exists, the function exists, and yet it's not continuous because they're not equal. Here is f of a. Okay? So it can't possibly be continuous. Indeed, if you actually want to draw it, you have to go there, take a break, come up here, and then go back down there. It can't possibly be continuous. So a continuous situation has to look like this. Something like that. Or what I had up there. Okay, that's all very well and good. Now, before I give examples of continuous functions, I said there are different flavors of continuity. I have to say where a function is continuous. So I've now told you what it means to be continuous at one single point. So what does it mean if I say f is continuous in some open interval, say ab? Right, that's all the numbers between a and b, but not including a or b. What does that mean? Well, that basically is true, or it means that f is continuous at every point in AB. Okay, so the picture of that, I don't know what the function does at A. It might even have an asymptote at B, but that's okay. This function is continuous on, as I've drawn it, on the open interval AB, because if you pick any point, it's continuous there. You can't pick A, you can't pick B, because it's an open interval. Okay, so when I say it's continuous on an open interval, I mean infinitely many statements. It's continuous here, 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 actually everywhere in between. So that's kind of nice. That's pretty powerful. So what about something like this? What if I close up the interval? Of course, I could just close one of the ends by including the endpoint, but what if I close it up? Well, look at this picture. Suppose I fill in this circle. That still doesn't close it up on both sides. Maybe I have to close it up here. So my intuition is this should be continuous, except that there's a jump to get to there. So let's look at a different example. Why can't I just say it's continuous? This looks like it's continuous. Right? It's continuous everywhere. Well, what about at A? Is it really continuous? Remember, it has to have a two-sided limit there. What's the limit from the left? You can't walk along this curve from the left because there isn't a curve. There's no left-hand limit there. That seems a little bit unfair because the function isn't defined there. So I only need actually a right-handed limit at this side, and similarly I only need a left-handed limit at that side, and then everywhere else I want it to be continuous. So let's define this as I've said it. This is true means, and it means three things. First of all, f is continuous at every point in the open interval. So it's continuous in the normal sense at every point inside. And then I want to say f is right continuous at x equals a. So right continuous, as I said, it just means that instead of this limit being two-sided, I only need a right-handed limit. Okay, so it's unfair, as I said, to make it a two-sided limit because the function doesn't even exist there. So I'll just make it a one-sided limit. And similarly, at b, I need f to be left continuous. So this is sort of technical stuff, but it's useful to know these definitions because we've been spending some time on limits. So this says that the left-hand limit as x goes to b from below is the value of the function at b. And again, both of these mean this limit has to exist, this has to exist, this has to exist, this has to exist, and they have to be equal. Okay, so now we know what it means for a function to be continuous on various different types of intervals. Of course, if it's closed there and open there, then you don't need the left continuity because b isn't even in the domain. It's a sort of mixture of this and this. Now, what do I mean then finally if f is continuous? What does that mean if I just say f is continuous? Well, what I mean is it's continuous everywhere in its domain, and that if its domain consists of any closed intervals as pieces, then it has to be left continuous at one end and right continuous at the other. Okay, so when I say a function is continuous, I really mean it's continuous everywhere on its domain, but with one-sided continuity where necessary. Okay, so now I'm just laying the groundwork for what I'm going to be talking about for a little while in terms of continuity. We needed these definitions. Now, as you might imagine, it's a big pain to check that functions are continuous. Luckily, most functions that we're dealing with are continuous. Okay, so I'd like to look at section 5.1.3 of my book. And in there, I try to talk about examples of continuous functions. So here is a beautiful, beautiful fact. If you add up two continuous functions, you get another continuous function. Of course, this is on their combined domain where they're both defined. You can't add up something where one of the functions is not defined. So with that proviso, yes, you add up two continuous functions, you get another one. If you take the difference of two continuous functions, you get another one. If you multiply two continuous functions, you get another one. What if you divide two continuous functions? Well, you do get another one, except that you can't divide by 0. So if I take a function like, say, sine x, okay, I haven't proved it, but it turns out this is continuous. I will actually be proving it in a sense next week. So just take it from me for the moment. That sine x is continuous. So is cosine x. Continuous everywhere. I mean, if you don't believe it, just look at the graph of sine x. At least see that it looks like you can draw it all in one sort of motion. You could just, obviously you have to go on forever in both ways, but, basically through any point, there's no jumps. Same with cosine of x. So what about the ratio of them? Sine x over cosine x. Well, that's tan x. We know it's not continuous everywhere, because if you draw the graph of it, it's got vertical asymptotes. Can't possibly be continuous at the asymptotes, because the function isn't even defined. So basically, it's continuous everywhere except where the denominator is 0. Okay, so basically then, what I'm trying to say is, if f and g are continuous, then f over g is continuous except where g of x equals 0. So here the vertical asymptotes screw you up, and that's exactly when cosine on the denominator is 0. Okay, and I already mentioned that f times g is continuous, and f plus g and f minus g. I'm not writing them down, but they're in the book, and there should be. You could also write them down from what I'm saying. Okay, so here's an interesting thing. Constants are pretty obviously continuous. In fact, you can prove that directly just by looking at the definition. The limit of a constant is just the number. And in fact, the function f of x equals x is easily continuous as well, because there the limit is just f of a, which is a, and the right is f of a, which is a. So this also is in the book, but it's so simple that I'm just saying it at the moment. So what can you do with the constant function 1 and the function x? Well, you can multiply them together, you can add them. In fact, you can make polynomials out of them. So all polynomials are automatically continuous. You know, why is x squared continuous? Well, x is and x is. So multiply those together, you get x squared. Why is x to the x cubed continuous? Well, it's just x times x times x. So of course it's continuous because x is continuous. How about x cubed plus x squared? Well, we just saw that x cubed and x squared are both continuous, and now we're adding them up. So it's still continuous. So all polys, in fact, all polynomials are continuous. I just proved that for you, although I didn't actually write it down formally. But given the products and sums and differences, that's all you need to get that polynomials are continuous. So this is pretty nice. So yeah, most of the things that you look at are continuous, but not everything, right? What about tan x? That's not continuous everywhere. 1 over x, that has a vertical asymptote at 0. So, you know, we can't take these things for granted, but most of the things we're going to look at are continuous. However, let's define a function here. And we've looked at this sort of function before last time. Actually, last time we looked at it with the square root of x, but I'm restoring the x. So it's x sine 1 over x when x is not equal to 0. Obviously, this can't be right when x equals 0, because I don't know how to take 1 over 0. Can't do it. But I'll just define g of 0 to be 0. So last time we actually saw the graph of this, or something. I guess we didn't do this one. We did the square root of x. But we saw sine 1 over x has those crazy wobbles as the closer you get to 0. Right? The zeros of this thing, the x-intercepts occur at 1 over pi. They occur at 1 over 2 pi, 1 over 3 pi, 1 over 4 pi, and so on. And without the x out the front, the function has to go between 1 and minus 1 each time. So it's sort of wobbling, 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 and it goes crazy. I'm not drawing it because we are dealing with x sine 1 over x, which, as we saw, should be, to understand this, you take the lines y equals x and y equals minus x, and you kind of use this to modulate the amplitude, as it were. It's squashing it down. It still goes really crazy, but with the wobbles, but they get less and less because you're multiplying by x, and when x is near 0, that means the result of multiplication is pretty darn small. Now, at 0, we're going to fill in this point, and it turns out this is an even function. I mentioned this. Oh, maybe I didn't mention it. Well, let me mention it now. Sine is odd, so if you replace x by a minus x, the minus will flow through to the outside. And then if you replace this x by a minus x, you'll get 2 minus signs, which will cancel out. So that's a good exercise. Prove that g is an even function. I just explained it in words, but it would be a good exercise to write it out. In any case, that means that the rest of the graph is just the reflection. Now, actually, last time we saw that the limit as x goes to infinity of such an object Well, maybe we didn't see it. I'll look at it later today. So let's not worry about the end of that graph. But I do want to look at what happens at the origin here. Okay? So, what I would like to ask you is, where is G continuous? This is the question. Where is G continuous? So I've given you that function of G. I've given you the graph of it, and I ask, where is it continuous? So we've got a lot of points to consider. Let's first of all consider sine is continuous. 1 over x is continuous when x is not 0. Okay, so how about sine of 1 over x? Well, that's not a product of the two functions. It's actually a composition of the functions. This is the composition of, first you do 1 over x, and then you take the sine. Well, it turns out that the composition of continuous functions is continuous, provided that the domains work out properly. Okay, so this is the composition so it's continuous except when x equals 0. It's continuous when x is not 0. Of course, 1 over x isn't even defined when x is 0. Okay. Also, x is continuous. So the product, x times sine 1 over x, is continuous too. It's a product of continuous functions when x is non-zero. Okay? So we've actually covered every single point except for 0. This function g is automatically continuous when x is not 0, because when x isn't 0, it's made up of these three building blocks which are continuous. 1 over x, sine of 1 over x, so the composition there, and then multiply that by x. So continuity is pretty resilient. If you take two things that are continuous and you don't get any screw-ups with the domain, and you mash them together somehow, composition, multiplication, then the result will be continuous. But what about at 0? Well, let's check 0 directly, because something weird happens here. Let's check 0 directly. What we need is the limit as x goes to 0 of g of x has to equal g of 0. And I will put a little question mark there, because we don't know that that's true. That's what we're supposed to show is true. See how nicely that chalk erases. I brought my own chalk today because the chalk in the room let me down. Now I can erase this without needing a degree in weightlifting. All right, so we've got to check that this limit is 0. Now, to do this, I'm actually going to do a bit of a review of last week's review session. So I want to, first of all, let's look at the right-hand limit. So this is just limit of x sine 1 over x, right? Because when x is, the right-hand limit only involves values of x that are bigger than 0. And when x is bigger than 0, that's what g is. In fact, when x is not equal to 0, that's what g is. Okay, so I've got to deal with this. And as we did last week, the squeeze principle, the sandwich principle, is the way to deal with this. Well, start off by writing that sine 1 over x is between 1 and minus 1. That's true of sine of anything, but it happens that we care about sine 1 over x. Now let's multiply by x. I claim that if I do this, I get the inequalities, but with x out the front. Now this is okay because x is actually positive. Anyway, the point is that consider the limit of this and this. So limit of as x goes to 0 plus of minus x, well that's just 0. And the limit as x goes to 0 plus of x equals 0. So because they both get squished together to 0, and this is in the middle, it also gets squished. Therefore, by the sandwich principle or the squeeze principle, the right-hand limit is 0. Okay, that takes care of the right-hand limit. I'll fill that in there. What about the left-hand limit? Surely the same argument works. Well, it does, but you just have to be a little careful. Again, when you're to the left of 0, the function is again x sine 1 over x. But I don't know what that limit is. Well, let's just start exactly the same way. Yes, sine 1 over x is between negative 1 and 1. However, if you're going to multiply by x now, which is fine, be aware that you need to reverse the inequalities. If you want to write down something that's correct, you have to reverse the inequalities. Note, x is less than 0, so reverse the inequalities. If you just write down this, that cannot be true for x negative. For example, when x is, say, minus 1, that's 1. How can 1 be less than or equal to something less than or equal to minus 1? That just doesn't make any sense. The inequalities would be the wrong way around. Whereas here, if x is negative 1, well, that's minus minus 1, so you get 1 is greater than or equal to this is greater than or equal to minus 1. So that is the correct way around. Of course, it doesn't make a difference because the sandwich principle doesn't really care which one's on the top and which one's on the bottom. That limit is 0, so that goes to 0. This goes to 0 up here. Therefore, again, by the sandwich principle, the left-hand limit, x sine 1 over x, is 0. Can anyone tell me, though, everything I've written down is fine. Can anyone tell me how I could have saved some time? Why this was actually obvious based on something I said earlier about the function? Anyone have any clue why you could just say in one word or one line that it's 0? Any ideas? Just throw it out if you have one. If you're watching online, you can just think of it to yourself. I can't hear you, I'm afraid. No ideas? Nothing? Come on, someone. Well, okay, I guess I'll have to tell you then. The answer is it's an even function, right? If it's an even function, it's symmetric. So everything on the right also goes for the left. So if this limit turned out to be 7 on the right-hand side, then the left-hand limit would be 7 as well. So in this case, it's 0, so the left-hand limit is 0. What if it were an odd function and the right-hand limit was 7? What would the left-hand limit be? Someone. Negative 7, right, because that symmetry works the other way around. Anyway, that just could have saved us a few little minutes' work. We're basically done. We've shown that the left-hand limit and the right-hand limit are both 0. So the two-sided limit, x goes to 0 of g of x, is the same as the two-sided limit of x sine 1 over x, which we've just shown is 0. And guess what? 0 is exactly the value of g of 0 by definition. So if I define g of 0 to be any other number, then it wouldn't be continuous. It would still be a well-defined function, but instead of plugging the hole over here, I'd have some other random number up here or down there or something, and it wouldn't be continuous. Okay, so actually you can't really draw this function because you'd have to jitter around too much, and it never actually gets to 0 in some sense, although it does actually get to 0. I don't know. I'm trying to say that just using a crude definition like, oh, you can draw it in one piece, doesn't cut the mustard when you're dealing with something as nasty as this. And yet, by using the math, you can see that it's actually you can see that it's actually continuous. Okay? So there's a whole bunch of continuous functions. I have one more comment to make before I move on to the next section. Last time, I looked at this limit, and it's not a very tricky limit. It's not a very tricky limit. Actually, the tricky thing came when x equals 2 there. But for this one, I said, oh, you can just substitute, right? Because there's no 0 on the denominator. I said, oh, look, you can just substitute like this. And if you work this out, you get 1 plus 3 plus 2 is 6 over minus 3, and it comes to be minus 2. Now, okay, nothing hard about that. But I also said a whole lot of times, okay, that the limit does not depend on the value at the point. Right? I've said this over and over again. The limit does not depend on the value, only the values near. And yet here, I'm just saying, oh, I want the limit as x goes to minus 1, so just plug it in. It seems like I was contradicting myself. Well, the actual answer is formed by continuity. Now that we understand continuity, there, the value of the limit is the same as the value of the point. So if you know a function is continuous, and you want to work out the limit at a point, well, it's just the value of the function at the point. So what's going on? This is a polynomial, so it's continuous. This is a polynomial, so it's continuous. So the ratio is actually continuous, except where the denominator happens to be 0. Well, at minus 1, this is totally fine. So basically, what am I doing here? I'm going to say let f of x equal x squared minus 3x plus 2 over x minus 2. All this equation says is that the limit as x goes to minus 1 of f of x is equal to what you get when you substitute minus 1 in there, which happens to be negative 2. Okay, so that equation, when you write something down, you actually plug it in and you get the answer, which sometimes works like it does here, you are actually using the continuity of the function. Even if you don't know it, or you don't care about it, that's what you're doing. So f is continuous, i.e. f is continuous at x equals minus 1. We're just using the continuity at minus 1. Okay, so of course it's not continuous at 2. And there you can't plug in because you get 0 over 0 and everything falls apart. Anyway, so that's just a little point. It's not made very often, and I thought that it would be enlightening, even though it does not actually affect your problem solving. It's a nice thing to see. Okay, so are there any other questions about what I've said? If you have one, then just start shouting it out as I'm erasing, and I will listen. All right. Okay, intermediate value theorem. That's the next topic. IVT, intermediate value theorem. I'm not even going to write out those words, but you're welcome to do it. Okay, so we've got these continuous functions. We've got to do something useful with them. Okay, we've done something a little bit useful with them here. We wouldn't have been able to do that limit as easily, but nevertheless, there are other properties that are nice, and we're going to look at two of them. The first one is called the intermediate value theorem, and here's the basic gist of it. Suppose that I have a function that's continuous, and I happen to know it's continuous, so say f is continuous on the interval, closed interval, AB. Okay, remember that means it's left continuous at A, it's right continuous at B, and it's continuous everywhere in between. Okay, so that effectively means I start here, I draw a line or a curve, and I'm not allowed to take my chalk off, and somehow I have to end up here. Well, the conclusion is that you must cross the axis somewhere. Now, of course, I could cross it multiple times, but I have to cross the axis at least once. So if f of A happens to be less than 0, and f of B is greater than 0, then f must have an x-intercept. At least one. And, of course, it has to be in the open interval a, b, because it can't be at a, because f is negative there. It can't be at b, because f is positive. So the x-intercept, or at least there has to be at least one x-intercept in the middle. Now, I can't prove this for you. It's actually quite tricky. But at least intuitively, it seems reasonable. It seems reasonable. There is actually a proof, I believe, in the appendix of the book. People in the room do not have the appendix, but it will appear in the final calculus Lifesaver, as it's going to be called. So I believe I put a proof of the intermediate value theorem in there. Anyway, but as I say, it's sort of intuitively clear. If the function were not continuous, it wouldn't have to be true. For example, here's a function that's not continuous. It's continuous except at one point. There. It's not continuous at that one point. Everywhere else it's continuous. And yet it screws up the whole party. The thing does not have any x-intercepts. In fact, even if it was not continuous just at the end point, that would be bad enough. For example, if it's not continuous at a, it could look something like this. No x-intercept. You started off at a, you immediately jump above the axis, and you keep on going. Well, f of a is less than 0, f of b is greater than 0, and the function is not continuous, and there's no x-intercept. Now, of course, there might be an x-intercept, but you can't guarantee one, right? I mean, sure, I could have had this dip down there. Oh, look, there's an x-intercept. Yeah, but that was just a fluke. So, another way of saying this, i.e., there is at least one number c there is a number c, i.e. at least one, such that f of c equals 0. So c could be here, for example, in this picture. It's just the x-intercept. Right? X-intercept means if c is an x-intercept, then f of c equals 0. Right? So that's one statement of the intermediate value theorem. Now, of course, what if they're switched? What if f of a happens to be above the axis, and f of b happens to be below the axis? Well, the same is true, also true, if f of a is greater than 0 and f of b is less than 0. Okay? As long as they have opposite signs, in fact. If one of them is positive and one of them is negative, that's good enough. Of course, if they're both positive, it doesn't have to go down. If they're both negative, it doesn't have to go up to the axis. But it does have to cross if one is positive and one is negative. Okay, so here's a fairly simple example. E.g., if p of x happens to be equal to negative x to the 5 plus x to the 4 plus 3x plus 1, show p has a 0 or a root or an x-intercept in 1, 2, in the interval 1, 2. Well, the correct solution to this goes like this. First of all, as a bullet point, p is continuous. In fact, all polys, all polynomials are continuous. But if you don't say that, if you don't explicitly say that, you shouldn't get full credit for this problem. Because you're supposed to understand that the intermediate value theorem only applies to functions that are continuous. And in fact, we actually need it only to be continuous on 1, 2, the closed interval. But it's actually continuous everywhere. So of course, if it's continuous everywhere, then it's also continuous on the interval we care about. So that's the first point. Second point, well, let's check p of 1. So you plug in 1, you get minus 1 plus 1 plus 3 plus 1, which I believe is 4. Now plug in 2. 2 to the 5th is 32. So you actually get minus 32 plus 16. Did I screw this up? This does not seem right. Minus 32 plus 16 plus... Oh no, it is right. It is right. That's 16 plus 6 is 10. Negative 10 plus 1 is negative 9. So if you substitute this in, you get that P of 2 is minus 9. So the conclusion is, therefore, by the intermediate value theorem, so you notice that P of 1 is positive, P of 2 is negative, so by the intermediate value theorem, P of C equals 0 for some C in 1, 2. So it's just a direct application of that theorem. Not very hard at all. Maybe it would be worth writing the words that P of 1 and P of 2 have opposite signs. And when I say sign, I mean S-I-G-N, not S-I-N, or S-I-N-E. Okay, any questions about that example? All right, let's look at something a little harder. I believe something like this came up on your homework. Show the equation x equals cosine of x has a solution. Well, let's first of all draw a little picture of what's going on. Cosine x looks like this. We drew the graph of it a couple of weeks ago. And y equals x. So this is y equals cosine x. Y equals x looks like this. So not only does it look like it has a solution, it looks like the solution lies between 0 and pi over 2. It actually doesn't look like it has any more solutions. In fact, if it did have any solutions, well, they clearly couldn't be bigger than pi over 2, because you see cosine is then constrained after this point between minus 1 and 1, whereas y equals x is bigger than pi over 2. So there's no way it could have any more. The only ones could be in this little region here. And, you know, it turns out there's only one. How do you actually prove, though? This is not a good enough proof just to show that, yes, it looks like it's right. We should be able to do it properly. Okay? Now, the way that I've said the intermediate value theorem, I only spoke of one function, not two. Here we have two, x and cosine x. Well, the trick is to put everything on one side and deal with one function. So put everything on one side. So, i.e., mentally, if we can solve x minus cosine x equals 0, then, of course, x equals cosine x has a solution. So we need this. We want a solution to this. Want a solution to the equation x minus cosine x equals 0. Okay, so let f of x, no one is going to do this for you. You have to take the initiative, put everything on one side, and you have to let f of x equal x minus cosine x. No one is going to call it f for you. You can call it any letter you like, but you have to write it down as something. Okay, f is continuous since x and cosine x are continuous in x, right? X because it's a polynomial, cosine x, well, I already mentioned that it was, although I said I'm going to prove it next time. Okay, so it is important, though, as I said, to state that f is continuous. Also, we think our solution lies between 0 and pi over 2, so let's check f of 0. 0 minus cosine 0. Cosine of 0 is 1. Don't forget that. Look, here it is. So 0 minus cosine 0 is negative 1. On the other hand, we'll check f of pi over 2. That's pi over 2 minus cosine pi over 2. And as you can see, cosine pi over 2 is 0. So this is just pi over 2. And actually, the best way to state this, and I'm going to put less than 0 here to emphasize that. I'm going to put greater than 0. And if we can just take a slight break, move back over to the other problem, and look back there, I really should have, the best thing I should have done is filled in that 4 is greater than 0 and that minus 9 is less than 0. So if you go back and fill that in, that's really what's important. The fact that it's 4, the only important thing about 4 is that it's greater than 0. And similarly, the only important thing about minus 9 is it's less than 0. So sorry, I forgot about that. Anyway, I've done the same thing over here. And so the conclusion is, by the intermediate value theorem, IVT, f of c equals 0 for some c, in fact, between 0 and pi over 2. Now, just to really emphasize it, if f of c equals 0, that means c minus cosine of c equals 0 for some c. And that means that c equals cosine of c. So whatever this mythical number c is, I mean, it's not mythical, I know it exists, I just don't know what it is. I know it's between 0 and pi over 2. But for this particular number of c, that is a solution of the original equation. So there it is in gory detail. Okay, but it is much trickier than the first one, because you had to do two things. You had to put everything on one side, and you had to baptize it, if you like, the function. I don't mean to get religious here. You have to name the function. All right, any questions about that example? Okay, well, let me just mention that although you can get by with everything that I've said, I've told you the theorem as it is, it works fine. The thing is that there's a little variation of it that's actually kind of useful at times. See, there's nothing special about the height 0. It could be any height between f of a and f of b. Right? 0 is not particularly important. You can replace it by m. So, for example, if f of a is less than m, and f of b is bigger than m, then you're guaranteed to hit height m. So, alternate version, if f of a is less than m, and f of b is greater than m, and f is continuous, again, well, I should have even said that first. If f is continuous on AB, and it has to be the closed interval AB, and if f of a is less than m and f of b is greater than m, then f of c equals m for at least one c in AB. So it's just the same thing as the previous statement, but 0 is replaced by m. And of course, it's also true if f of a is greater than m and f of b is less than m. Okay, so of course, you don't ever need this version of it, because if you put everything on one side, you always end up with a 0 on the right. So actually, this reduces to the earlier version very easily. But here's an example where you can actually use it directly. Show 3 to the x plus x squared equals 5 has a solution on 0, 2. Okay, well, I could just subtract 5, and then I would have something equal 0. But you don't even need to. I can just say, let f of x be equal to 3 to the x plus x squared. Well, exponentials are also continuous. I can't prove that until a little bit later, but it's not going to be next week. But again, take it on some sort of faith for the moment, plus combined with the fact that the graph looks like it's continuous. This is 3 to the x. So f is continuous. Sum of exponential f and poly, both of which are continuous. And so the sum is continuous. F of 0 is 3 to the 0 plus 0 squared, which is equal to 1. F of 2 is 3 squared plus 2 cubed. No, 2 squared, which is 13. What's important about 1? It's less than 5. 13 is bigger than 5, So together, by the intermediate value theorem, f of c equals 5 for some c in 0, 2. Or 0, 2. It's also true for some c in 0, 2 closed. It's just we know it's not at 0 or 2. So this is actually a stronger statement. So that's all I really want to say about the intermediate value theorem. There's a tough example in the book, tougher anyway, about showing that every odd degree polynomial has a root. And that's in section 5.1.5. And I urge you to look over it. It's not very, very long. But truth be told, it's probably harder as a question than you could reasonably expect to find in Math 103 or indeed most college courses. So I will not spend time on it here. Yes, question? Well, the question was handily given to me that showed that it has a solution at 0 and 2. Now, if it hadn't been, like in the case of the cosine one, sometimes you just have to flounder around, either by trying to draw a picture or trying to, or just actually plugging in values and see what you get. I mean, the fact is, here's 3 to the x, here's x squared, but I don't care where they're equal. I actually want the sum of them. So the sum of them is going to look something like this. And so, yeah, I mean, it's going to have a solution somewhere around here. I just don't know where. It's clearly, it looks like it has another solution somewhere negative as well. And you could try to identify it by, plugging in various values. But you won't actually find out what it is. All you can do is find out a region where it is by showing that 1 is greater than 5 and 1 is less than 5. Okay? Cool. How are we going for time? We are always running out of time. Okay. So, moving on a little bit. In section 5.1.6 of the book, I look at this max-min theorem. I'd like to just spend a little bit of time on it, but I can't really think up any problems yet that are going to use it. When we sketch curves and stuff like that, we'll be using it. So here is something called the max-min theorem. I just want to sort of state it briefly and then move on. And I think the next thing on my agenda is differentiability. And I'll spend a little time on that, and then I'm going to have to do trig limits. Okay, so max-min theorem. Here's what it says. If f is continuous on a closed interval again, it's vital that this be closed here or else the theorem is not true, then f has a maximum and a minimum. It is a max and min theorem, really. So what do I mean by a maximum? Well, C is a maximum for f if f of c is bigger than f of x for any other x, or even any x at all. If x is c, of course, then this is equal. So the picture is pretty clear. Here's A, here's B. The thing's continuous. This is the maximum. C. C is the maximum here. And here D is the minimum. So it's the highest. It's a limbo game. How high can you go? Actually, limbo game is how low can you go. So that's the minimum here. Now, I don't say it can only have one. It could have multiple. That's a max. That's another max. By the way, the maximum is actually the x value. It's not the height. I say that c is a maximum if f of c is as big as it can be. F of c is the value, or the value of the function at the maximum. But call that c1, c2. This is f of c1 that happens to be equal to f of c2. Okay, so I just want to spend a few seconds about why this is sort of profound, or I'm not even proving it again. It's kind of hard to prove, but I would like to show you when it can go wrong. Well, first of all, you might think it goes wrong if the function is constant. Where's the maximum? Well, actually, every point is a maximum. Every point is at least as big. F of c is at least as big as everything else. Okay, so it's equal to everything else, but that's why I put a greater than or equal to. So every point here is a maximum, and every point is a minimum. Is a max and a minimum. Okay, so not only does it have one maximum, it has infinitely many maxima. And same with the minimum. Okay, but what if the function is not continuous? Well, here's some examples of what could go wrong. And I'm just going to draw a few diagrams. Okay, so here's a function that isn't continuous. It's continuous everywhere except this one point somewhere in the middle. Why doesn't that have a maximum? Because it just goes on up and up forever. There's no one point that's higher than any other point. You can always find a higher point by going closer to the intercept. Same with the lower. There's no minimum because you can just keep going closer and closer to the intercept. Here's a more subtle example. Okay, there's a function that's continuous on the open interval AB, but not closed. I said closed was important. It does happen to have a minimum at C, but where's the maximum? Who thinks that there's a maximum at B? Who thinks there's no maximum at B? The rest of you, no opinion? That's okay. Actually, there is no maximum at B. For there to be a maximum at B, f of B would have to exist. It doesn't even exist. But can't it be the point a little bit to the left of B? Well, there is no closest point to B that's a little bit less than B. It doesn't exist. I can always go halfway in between, and then I'll get a higher point. So whatever you think is higher, whatever you can do, I can do better. Of course, then you can do better. We can keep on doing better. But we can never do best, because there's a hole there. Okay, so that's a sort of subtle fact. And again, the one other little case is, here's a function that happens to, by luck, have a maximum here and a minimum there. But it didn't have to. It didn't have to. Here's a function with neither a max nor a min. You want this to be the min, but it doesn't exist. You want that to be the max, but it doesn't exist. You cannot get, actually, you could keep on going and going. No matter where you stop, you can always go closer without actually getting to that point. So basically, you should just know the statement of the max-min theorem. But this is really going to come into its own when we start learning about how to find the maxima and minima. All I'm saying is that there is at least one. We'll use the derivative to find it. So that is actually a nice lead-in to differentiation, which is my next topic of discussion. And luckily, I'm not going to spend that much time on it because I need to do some trig limits as well. So, but any quick questions about the max-min theorem, just theoretically? All right, well, let's move on to section 5.2. Now, I've said that it's nice when functions are continuous. There's actually, you can do better. You can not only have something that you can draw without taking your pen off the page, you can also have something that doesn't have any sharp corners, like the absolute value of x. I want to avoid this, and so I'm going to talk a little bit about differentiation. But first, I just want to spend about 5 minutes on some physics ideas, because they actually inspired the whole thing, and soon, next time, we'll actually look at some problems in physics that we have to know how to solve. So I'd like to talk a little bit about average speed. There's a more thorough description in my book, but for the moment, I just want to imagine that you have a particular, just think of a car driving back and forth along a straight road with mile markers that have a 0 and a -1 and a 1. It's just like a number line. I've never seen mile markers that were negative, but let's just imagine that you could actually have that. Okay, so when I write something like speed equals distance over time, I don't really mean speed, I mean average speed, right? Because no matter how short a time period, I might have been going at different speeds, right? I might have my accelerator down or the brake on, and so for this to make sense, I mean an average speed over a time interval. Now, that is a very sort of simple concept. There's actually a better concept that I want to talk about called average velocity. We'll be using speeds and velocities, so it's important that we know what this means. The definition of this is that it's displacement over time. Now, what's the difference between displacement and distance? There's two differences. One is that displacement can be negative, but another difference is that displacement only depends on where you start and when you finish. It doesn't matter how you got there in between. So, in fact, displacement equals final position minus initial position. Okay, so you observe this car at one time. Oh, it's at 3. And then a little bit later, oh, now it's at 1. Well, the displacement is 1 minus 3. So it would be negative 2. And then if you knew how long it took, you could divide that by the time, and you would get the average velocity for that period, which in this case would be negative. So velocity can be negative. Okay, so again, the distance, it could have been 2, right? To get from 3 to 1, it could have just gone straight there. But it might have gone sort of backtrack, back and around, and if you just looked at it now and looked at it there, I don't know where else it went in between. Right? So the distance depends on the path, whereas the displacement just depends on the beginning and the end. Okay, so those are two sort of distinctions here. And it's actually possible to have an average velocity of 0 even if you've been moving all the time. Here is an example. Okay, start the clock. Stop. What's my average velocity? Well, I started at the same place as I finished, so my displacement was 0. So my velocity was 0. Average velocity was 0 over the time. But clearly my speed was not 0 the whole time. Right? I moved around, and yeah. Okay, so the average speed and average velocity are related, but they're not the same thing. One thing that is for sure is that if you're always going in the same direction, then the average speed is the absolute value of the average velocity. Right? But if you change direction, as you saw, I moved back and forth, that can screw the whole thing up. So that kind of just goes through sections 5.2.1 and 5.2.2 very quickly. But now, here is the rub. What I want to do is define my velocity at an instant of time. I don't just want what the average is. I'm interested in a particular moment of time. So think about this. Car goes by. You take a photo at a really short exposure time. You know, it's a digital camera, really quick. Bang. Car looks like it's still. How fast was it going there? There's no way to tell. If there's a little bit of a blur, you might be able to tell, but if it was a really, really, really quick exposure, you can't. But if you had another photo a millisecond later, you could at least work out the average velocity over that millisecond by looking where it was now and then where it was a millisecond later. And then you can take the displacement, you can divide by the time. Well, even a millisecond, the car could change its speed. So you've got to make it a nanosecond and a picosecond. And so clearly, in order to get some real definition, we're going to have to use a limit. Okay, so in order to quantify this, here's the idea. Just let f of t equal the position of the object. I'll call it a car. Car at time t. Okay, so there's different. If I plug different times in, I can find out where the car is at that time. Okay, so I know the complete motion of the car. What I want is the velocity. So the average velocity between time t and u. So t is what I'm interested in. I'm going to let u be a little time later than t. So what should that be? Well, the displacement is the final position. So we started at time t, but at time u, the car is at position f of u. And then I've got to subtract the initial position, that is f of t. So the car goes from position f of t to position f of u. How long does it take to do it? Well, started at time t, went to time u. The difference between those is the length of the time interval. Okay. And actually, if you think about it, this is even true if u is before t, believe it or not. Well, that means, see, if u is before t, then both the top and the bottom can be reversed. We can actually do f of t minus f of u over t minus u. We can just flip them around, and the ratio is still the same. All right, so that's actually true regardless of which order u and t come in. Now, what I really want to do is let u be really, really, really close to t. And that is where a limit is. So actually, I'm going to say that the instantaneous velocity, so the velocity at an instant, which actually, is basically what you see on your speedometer as you're looking at your car when you're driving. So you're not a stranger to instantaneous velocity. If I say the car is going at 55, I mean right now. I don't mean average. So we say the instantaneous velocity at time t is the limit of the average velocities over really short time periods. Limit as u goes to t of f of u minus f of t over u minus t. And here, u is now a dummy variable. T is the time I'm interested in, but u is just some other time that I'm letting get closer and closer to t. So the answer does not involve u. It only involves t. Now, that's actually one way of writing it. But you can also do a substitution. If you let u be t plus h, the advantage of this is that h is now the difference in time. It's how much you have to add to t, or take away from it if h is negative, in order to get to u. And if you do this, let's look what happens. As u goes to t, well, h is equal to u minus t. So as u goes to t, h goes to 0. The difference, u goes to t, u minus t goes to 0. So this equation can also be written, I'll write or, limit h goes to 0, u is equal to t plus h, and the denominator is just h. The denominator is just h, because u minus t is h. Okay, so that's another way of writing it. So this is what we mean by instantaneous velocity. Now, of course, this is a derivative. What do I mean? Well, let's look at a different problem. And here's the... Well, it looks like a different problem. We have some axis here. I'll call it the x-axis as usual. And we have a function. And we've got to pick a particular point, which I guess I'll still call x. And I'd like to know what's the slope of the tangent at that point. So this is the sort of nice problem. I don't even know what the tangent actually means. But we think it's something that intersects the curve once, except that it doesn't matter if it intersects it somewhere out here. It just has to be once when you're close by. But we also don't want it to go through. So we haven't really defined tangent. It sort of has to touch it. Well, now we're going to make it a little more precise. You see, let me redraw the picture a little bit with a different function just to get more clarity here. If this is x and this is x plus h, I could actually draw the so-called secant between them. And the slope of it is actually very easy to calculate. The slope here is the rise over the run. Well, the rise is f of x plus h minus f of x, because I've gone from height f of x up to height f of x plus h. And the run is just h. This is the distance here. So without getting into too much fantasy, well, look, it's pretty similar. The difference is the limit. See, the tangent that we like, this is the tangent that we want. We can't just find it directly because we only know one point it passes through. So the best we can do is to let h be smaller and smaller. And so this line comes in and in and in. And if you pick 2 points that are very, very close, you'll get a line whose slope is very, very close to the actual one, but you will never get the slope of the actual one. Well, you could if you were lucky, but in this picture you will never actually get the correct slope. That's where you need limits. So this is the first sort of big thing in calculus. We started off with limits, which is a tool, and the first thing we're using them for is to get instantaneous velocities and slopes of tangents. So this is the slope of the secant. Now, let h go to 0, and I will say that the slope of the tangent, whatever the tangent is, we only have a fuzzy idea of what this is limit as h goes to 0, f of x plus h minus f of x over h. Beautiful. It's the same as the instantaneous velocity. So in fact, the instantaneous velocity, if that is a picture of where the car is at any time, so if you now interpret the x-axis as time, then the slope of the tangent gives you the velocity. Now what does this have to do with this idea of derivative? Well, in fact, I'm going to define the derivative. So here's the definition of f, of the derivative of f. It's defined by this equation. It's exactly what I just wrote. Limit as h goes to 0, f of x plus h minus f of x all over h. Now, that limit, just like any other limit, does not necessarily have to exist. So let me just say if limit exists. Otherwise, undefined. Okay, so I just want to sort of review the basic idea of the logic. Where's my chalk gone? Oh, here we go. So we start off with the function f. We try to find that limit, and you get a different limit for each value of x. Remember, it doesn't depend on h, because that's a dummy variable that just goes to 0. But you get a different limit depending on which x you use. So that means that this value, f prime of x, depends on x. Another way of saying that is that f prime is a function. So the derivative, f prime, is itself a function of f. A function of x. Okay, so we start off with a function of x. We get a different function of x. Another way of looking at it is that the slope of the tangent is different, or might be different, for each value of x. And you can see it on this picture up here. You know, this has a certain slope, but there's a different slope here, a different slope here. This slope here at this point x is what f prime of x is. But if you change x, you change the slope. So here's a really simple example. Suppose f of x is 15x squared plus 7. Well, according to this, f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. That's just the formula, which happens to be the limit as h goes to 0. Now, what is f of x plus h? Well, it's 15 quantity x plus h all squared plus 7. And then I've got to subtract f of x itself. So that's 15x squared plus 7. And all that over h. Now, if you just try plugging in h equals 0, you'll actually get 15x squared plus 7 minus 15x squared plus 7. So you get 0 on the top over 0 on the bottom. So this is, by definition, an indeterminate form. Remember, 0 over 0, you've got to work harder. You've got to do something clever. And in this case, it's not very clever. All you have to do is expand this out into x squared plus 2xh plus h squared. And in the interest of time, I will just sort of mentally cancel out the 15x squareds, and I will mentally cancel out the 7s. And it is worth checking for yourself that what you end up with is actually 30xh, so that's the 15 times 2, plus h squared over h. Now, the beautiful thing is that although it's 0 over 0, you can divide by h. Remember, h is not actually 0, it's only going to 0. So you can divide top and bottom by h, and you can get 30x plus h. Now remember, it's the limit as h goes to 0, not as x goes to 0. So this first term is sort of impervious to h, it just stays as 30x, but the second term goes to 0. So in the limit, this is 30x. So what does that actually mean? That means if you graph this thing at height, it's a sort of parabola, quite skinny parabola at height 7. Well, suppose I take the value 1 and I go up here. How steep is this tangent here? Well, it's 30. That is a line of height 30. What about at minus 2? I go up to there. I get an even steeper but negative line. It's got to have a negative slope because it's downward. Well, what's the slope at minus 2? Well, negative 60. It's just 30 times the x coordinate. So actually, that one formula, 30 f prime of x equals 30x, gives me the slope of the tangent everywhere on the curve. Any tangent you choose. You just double the x coordinate, and actually not double it, multiply it by 30 rather, and you will get the slope of the tangent. Pretty neat, huh? Well, it's pretty neat. It took humanity up until the 1600s to think of it. So the ancient Greeks only had a very dim idea about this, although they were pretty smart. They knew a lot of stuff, but they did not know this. That one little thing unlocked basically most of modern technology. So do not underestimate the power of what I've just shown you. Or the dark side, if you prefer. No, this is all good. This is all good. Okay. So, someone asked about the absolute value of x, and I finally get to answer it. I like to consider f of x equals the absolute value of x. And I want to remind you, as I have done for each of the previous 2 weeks, that you can write this as x when x happens to be bigger than or equal to 0, and minus x when x is less than 0. So if we graph y equals x, it looks like this. And if we graph y equals minus x, it looks like this. And according to this, when x is greater than or equal, we want x, so we'll fill in that piece. But when it's less than or equal, we want this piece. So it should be quite clear that when you're to the right of 0, you're dealing with a straight line of slope 1. Well, a very simple calculation shows you, in fact, maybe I should do that. Oh, I'll do it very soon. But a simple calculation, man, time just runs so quickly, for me anyway. A simple calculation shows you that the derivative is 1 everywhere here, because it's the same as the slope. The tangent here is just the line itself, anywhere there. So it's actually easy to see that f prime of x has to equal 1, because that's just the slope, if x is bigger than 0. And that it has to equal negative 1 if x is less than 0. But what about at 0? Should the function have a tangent there? It has a sharp point. So there's nothing that looks like it just hugs the curve, because it's unhuggable. It's a very angry curve at that point. It's not even a curve, it's just a spike. Who wants to hug a spike? Anyone? Anyone want to hug a spike? Because I can arrange it. I have some spikes just in my bag over there. We could do a demonstration. You could be on the video. No spike huggers? Okay, I don't blame you. Who wants to hug a spike? Okay, so anyway, the point is that there is no tangent. In fact, if you look at the right-hand limit as x goes to 0, of h goes to 0, rather. Well, let me be more precise. If there is a derivative at 0, f prime of 0, according to my formula, has to be the limit as h goes to 0 of f of 0 plus h minus f of 0 divided by h. How come I've got these zeros? Well, if you look at the definition of f prime of x on that previous board, you'll see all I did was replace the x's by 0. So in this particular case, I get the limit as h goes to 0. F of h is the absolute value of h. F of 0 is just 0. And so we get this. And we've actually looked at that limit before, and we've decided that it does not exist. Because the right-hand limit equals 1. but the left-hand limit equals negative 1. That's consistent with what I wrote up here, where to the right the derivative is 1, and to the left the derivative is negative 1. So basically, the limit does not exist. So f prime of 0 is not defined, or does not exist. 0 is not in the domain of f prime. So another way of saying this is f is not differentiable, cannot be differentiated at x equals 0, but it is differentiable everywhere else. Ooh. Okay, so that actually was in section 5.2.10. Now, I have so little time, but there are just a few other things that I need to talk about. What can I do? Okay, so here is one cool thing. A little bit of a diversion, apparently. First of all, if f of x equals x squared, I claim f prime of x is 2x. I'm not going to prove it because the argument is exactly the same. It's just without the 15 and without the 7. And if you don't multiply the 15, that got multiplied by 2. Well, if there's no 15, you'll end up with a 2. Just try it for yourself and see. Now, I'd like to show you a simple application of this, which we'll look at in more detail. Basically, if you look at f of x plus h minus f of x, that's the change in the y coordinates, right? We had a graph here. Bang. Here is x plus h. There's f of x. And there is f of x plus h. Okay, so this is actually the change in the y coordinates. So I would like you to allow me to write this as delta y. Okay, delta is a Greek letter. When it's done in its capital form, it means change in. And I don't want you to think this means delta times y. It's not. It's like delta y. It's just one object. It's the change in y. Well, why did y change? Because I changed x to x plus h. So h is actually delta x. This is the change in x. I changed the amount x to x plus h, and that was a change of h. So I'm going to write that as delta x. So the ratio of these two things is delta y over delta x. This is the change, or the ratio of change in y to change in x. And this is what a derivative is all about. So I want to just look at this, because this is not always covered, and I kind of want to just spend a few minutes on this. So look, here's what I'm trying to drive at. According to what I've said, the derivative is the limit as h goes to 0, but h, of course, is just delta x, of delta y, delta x. Another way of looking at this is that, i.e., if delta x is small, so if I don't change x by very much, then delta y over delta x is approximately equal to f prime of x. Okay, so the slope, f prime of x, is approximately equal to the ratio of what you get, the response in y, when you change x a little bit. Well, what the hell does that mean? Let's suppose y equals 2x is equal to x squared. And I want to just concentrate what happens when x is 6. Well, what's y then? It's 36. Okay, no problem. What about when x is equal to, what do I want to do, 6.01? What's y equal to? Well, if you had a calculator, you can work it out. And even without a calculator, it's a fairly simple bit of arithmetic. But I'd just like to, if you had to do a very, very quick guess, what should it be? Well, it should be 36 and a bit. Well, what's the bit? Well, according to this, the derivative, f prime of x, is 2x. And remember, that means that the change in y should, over the change in x, should be approximately 2x. Or another way of looking at this is that the change in y should be approximately 2x times the change in x. And I want to just use this last part of the formula here. How much have I changed x by to get from 6 to 6.01? I've changed it by 0.01. Now, multiply this by 2x. X is 6, so let's just write that 2x is 12. So 12 is our magic number. That means that y is approximately equal to 36 and 12 times this. Because 12 is the multiplication, it's the scale, if you like, the magnification. So I took 0.01 and I scale it up by my magic number 12, and I get a pretty darn good approximation for 6.01 squared. In fact, the true answer is, I worked this out earlier, 36.1201. So I was right to 2 decimal places. But you don't just have to do this. What should 6.004 squared approximately be? Well, you take the 36, which is your sort of base, you take this change, 0.004, and multiply it by 12. And you get 0.048. 4 12s are 48. And the actual number is 36.0. Oh, hell. In my book, I actually have 3 zeros here. So I have an extra 0 there, and that's all I know what the square is. I apologize for that. So it's actually this. Okay, but you see, we have an excellent approximation here. And we understand it in terms of a derivative, right? I start off with 6 squared equals 36. I nudge the 6 by a little bit, and the corresponding nudge on the 36 side is 12 times as much. Because 12 is the value of the derivative. All right. Man. Okay, so the only other comment I have is that 12 is the magic number when you're at 6, but it is not the magic number when you're at 13, for example. What should 13.002 squared be, approximately? Well, 13 squared is 169, but how much extra do you add? It's not 12 times 0.0002. You see, the derivative, again, was 2x, and that's because f of x is x squared, and we're squaring. Of course, if you cube, everything changes. But we're just squaring. So, at 13, the magic number is actually 26, not 12. So this should be approximately 0052, because 26 times 0.0002 is 0.0052. Okay, so it's a different magic number when you're close to something else. And of course, the actual number just turns out to be 005200004, and I can't even remember if it keeps on going, but you see how close the actual approximation is. Okay, so inspired by this observation that the derivative is like a ratio, we say that f prime of x is the limit. We already know this. And we, instead of writing the delta, we write dy dx. So this is true if y is an abbreviation for f of x. So, you know, functions can sometimes be written f of something, or sometimes you just say y equals x squared, and that means y is a function. And in that notation, dy dx is the same thing as the derivative. So it actually means the limiting ratio of a small change in y divided by a small change of x as both changes become very, very, very small. Now, here's the thing. This is not a fraction. It's not a quantity dy over a quantity of dx. This is a fraction, and we're taking the limit, as delta x goes to 0. So it's really the limit of a fraction. Okay, it's worth knowing that this is the limit of a fraction, not a fraction itself. Luckily, though, it behaves in many cases as if it were like a fraction. The chain rule is the biggest one of these, but we're not going to do that this time. do it next time. All right, so there is an alternate notation. And now all that's left for derivatives is just to quickly go through and to tell you that there is a thing called the second derivative. I better mention that. So you start off with the function f, you take its derivative, you get a new function f prime. Well, you can repeat the process and you can get a second derivative, f double prime. You can differentiate again and get f 3 primes. Of course, that actually gets annoying to put 50 primes in there. So another way of writing that is you can actually put a little 3. So that means the third derivative. Actually, you could put an f2 here. You could put an f1. And the function itself is actually 0 derivatives of f. And of course, you can keep on going with 4 derivatives. You can write 4 primes if you like, or you can, these are called primes, so 4 apostrophes, 4 primes. So that's just some notation. We'll do plenty of calculations involving this, and we'll understand what the second derivative actually helps us understand. We'll look at what it helps us understand about the function. I should mention also that if you start off with y, the first derivative is dy dx. The second is written d2y dx squared. It's sort of weird that you write it. Why would you write the 2 like this? Well, another way this can be written is d dx of y. So this means the derivative with respect to x of the quantity y. And so this would be written d squared dx squared of y, the second derivative with respect to x of y, and so on, d3y dx cubed, etc. So again, I'm not giving too many examples of that. There's one other fact. I would have loved to have time to prove it and discuss it, but I don't, so I'm just going to state it. And this is in section 5.2.11, if you want to actually learn why this is true. But I have no time. Here is a lovely, lovely fact. If f is differentiable at some point x, then it's continuous there. At the same point. Now remember, for it to be differentiable, you need that certain limit, f of x plus h minus f of x all over h, to exist. So of course, f has to be defined at x for it to be continuous. But it's not totally obvious that just it being differentiable means it's continuous. Nevertheless, you can prove that that's true. Yes, a question? Nope. So this was not continuous. Not continuous. It's not differentiable either. There's no... It's differentiable not only when it meets, but that there's a nice tangent that hugs it. Okay? Now, I've said that if it's differentiable, if there's a nice tangent that hugs it, then you have to be able to draw it in one piece. It's continuous. So it sort of makes sense if you think about it. If there's a tangent that hugs it, then how could it be like this? There's no tangent there. What would it be? Even if it was nice and smooth here and nice and smooth there, they don't match. Can't be differentiable. Now, the converse is not true. You can be continuous without being differentiable. And we've already seen an example of that. Absolute value, it's continuous here, but not differentiable. Not diffable. It's continuous, but not differentiable at the origin. Okay? So the converse of the theorem is not true. A function could be continuous, but not differentiable. But if it is differentiable, it must be continuous. And that's actually how I'm going to prove next time that sine x is continuous. The easy way to do it, actually, is to find its derivative and say, yes, it has a derivative everywhere. So guess what? It's automatically continuous. You don't even have to check anything. It's differentiable. So the idea is that differentiable is somehow stronger than continuous. It's better, right? It's more exclusive. It's like, oh, you're continuous. I'm differentiable. I'm continuous as well, but I'm more than continuous. I'm smoother than you are. Smoother. Yeah. Question. That's a very good question. Remember we did left and right hand continuity. So I'm not going to have much time to say it, but if you replace the limits, either delta x or the limit h, remember I did f of x plus h minus f of x, if you replace that by a right-hand limit, you get right-hand differentiability. And if you replace it by a left-hand limit, you get left-hand differentiability. So if you want differentiability on a closed interval, yes, you play the same game, but instead of the limit of the function, you look at the limit of that ratio, f of x plus h minus f of x over h, and you look at a one-sided limit. It's a good question. All right. Very good. So that's what I wanted to say about Chapter 5, which means that in the last 25 minutes or so, I want to do half of Chapter 7. So I'm skipping Chapter 6 and moving on to Section 7.1, which is about trig limits. And I will do as much of this as I can, and I'm just going to have to stop in about 20-25 minutes. Okay, so let me tell you a little bit about trig limits, and this is going to be very problem intensive. Okay, I'm doing almost no theory here. I want to look at 4 limits. Let's just start off with 2 though, and I'll put up the other 2 in a second. So limit sine 5x over x. They look almost identical. The only difference is one of these limits is as x goes to 0, the other one is as x goes to infinity. And my friends, although it is almost the same in appearance, they are completely different in answer, in problem-solving techniques. They are just nothing alike. Okay? So you've got to distinguish what's going on. In this case, x is a very tiny number. Again, tiny, small, I mean near 0. So here, I'm taking sine of 5 times a tiny number. It's still a very, very small number. If x is 0.00001, even 5x is 0.0005. It's still tiny. So this is sine of a small number. To calculate this limit, you'd have to look at small values of x, small values of 5x. Whereas here, it's a large number. And so there's a big difference between sine of small and sine of large. Okay? Now, you might think, oh, that means whenever I see a x goes to 0, I'm dealing with a small. Well, not true. Check out this limit. When x goes to 0, 5 over x is a huge number. Actually, if x goes to 0 from above, it's a huge positive number, and if x goes to 0 from below, it's a huge negative number. But it's certainly not small. This is large, positive or negative. Plus v is positive, minus v is negative. Whereas the limit as x goes to 0, infinity rather, of the same quantity, x sine 5 over x, now when x is huge, 5 over x is small. So this thing we're taking the sine of is actually small. So do not fall into the trap of simply looking at where x goes to determine whether you're in the large or small case. You actually have to look at what you're taking the sine of, or the cosine of, or the tangent of, depending on the question. Actually, we've done this question earlier today. Sure, we did it with x sine 1 over x, but the 5 doesn't make a difference. We just used the squeeze principle. That limit we've already done. As far as I'm concerned, I mean, sure, you have to change the 1 to a 5, but that actually equals 0. We saw that earlier. But we still have to do the other limits. Now, I'd like to concentrate on the small case first. And then I'll come back to the large case. Luckily, the large case is just the sandwich principle, and we've already spent a lot of time on it. But I kind of want to spend some time on the small case, which is 7.1.1 and 7.1.2 in the book. Okay, so I'm going to spend most of my energy on that. And if somehow I don't get to the large case this week, I'll just wrap it up very quickly next time, and it will only take a few minutes because we've done it basically already. Okay, but let's spend a little time on the small case. Here is the fundamental limit that we're going to concern ourselves with. And you've seen this now in your class, but here it is. I cannot stress the importance of that limit. It's enough. It is a really important limit. And I'm not going to prove it. There is a proof in 7.1.5 of the book. It's not examinable in at least Math 103, but nevertheless, I would urge you to at least take a look at it. The only way you can prove this, as far as I'm concerned, is with some geometry, because sine depends on geometry, right? It's opposite over the hypotenuse, so you're going to need some triangles, you're going to need some geometry, and it's all just about areas and stuff, and it's pretty cute. But here is a sort of rationale of what's going on. Here's the graph of y equals x, and here's the graph of y equals sine x. Now, no one is going to say that these two functions are equal. Sure, y equals x is up here, sine x is down there. If this was actually true, this would mean that sine x equals x. Just multiply both sides by x. That's never actually true except when x equals 0. Even though it looks like these are very, very close, they actually only come together and cross at 0. So the interesting thing is that this actually means that sine x is very close to x. It's almost equal to x when x is small. And it is equal to x when x equals 0, but basically sine x is approximately equal to x. So if you took your calculator, put it in radian mode, of course, and take 0.0003 and hit sine, you will get a number very close to 0.0003. It'll be like 0.002998 or something like that. Right? So sine of a small number is approximately equal to the number itself. Another way of looking at it is this is actually the tangent at 0 to sine x. So this is related to the derivative of sine, but more on that next time. Anyway, that's my fundamental limit. Let's look at a few little varieties of it. As I say, there is a proof in the book, but you're just going to have to look at that. Or, of course, email me if you have any questions about it. Right. So, sine is not the only trig function. How about cosine? Well, it turns out cosine's a little bit different. Forget cosine x over x. Just look at cosine x. Plug in 0, and cosine of x is 1. Well, cosine 0 is 1, and cosine is continuous, as I've been saying, so that limit actually turns out to be true. What about limit, as x goes to 0, of cosine x over x? Why not look at the same thing? Well, that doesn't work as nicely. Sine x over x is like 0 over 0, so it's an indeterminate form. But this looks like 1 over 0. So the graph of this, it has an asymptote at 0. Whatever it looks like, it has this asymptote. So this does not exist. The right-hand limit of this is infinity. And the left-hand limit equals minus infinity. It's not particularly interesting. Right? It's infinity because you get like 1 over 0. But on the left-hand limit, you have like 1 over a negative tiny number, so you get minus infinity. On the other hand, so you might as well remember that. But don't worry about cosine x over x. On the other hand, tan x over x works nicely as well. This one's not too bad. You don't need to do any more geometry or anything like that. You can just do this. See, tan x is sine x over cosine x. And so I'm going to just write it like this. This piece goes to 1. This bottom goes to 1. That's just this. And so this is 1 times 1 over 1, which is 1. So basically, here's a limit that I think you should just be able to quote. But if you feel like you shouldn't assume this, but you're only allowed to assume the sine x over x, well, the proof is very quick. And you could just start off your exam paper or the question by saying, okay, well, tan x over x is 1 in the limit, and it's very easy to see why. Personally, I think that should just be something that you can quote. Okay, now, that's the basics of the thing. Now, however, here's where it's most useful. It's not just true for x, you could replace x by any other quantity. For example, the limit as x squared goes to 0 of sine x squared over x squared is 1. I just took the idea that sine of the small quantity over the same small goes to 1. Limit sine of small over same small as small goes to 0 is 1. It doesn't have to be x. It can just be any quantity that's going to 0. Now, of course, you don't normally want to write limit x squared goes to 0. The nice thing is that you can just write the limit as x goes to 0. So as long as these match, you're in great shape. As x goes to 0, also x squared goes to 0. But you've got to be a little bit careful sometimes. Look at this. The limit as 1 over x goes to 0, say plus, I'll just put the plus for the moment to avoid a technicality, of sine 1 over x divided by 1 over x is 1. That is absolutely true. As 1 over x goes to 0, say from above, sine 1 over x divided by 1 over x goes to 1. But what does it mean to say that 1 over x goes to 0 from above? Well, that means that x goes to infinity. So you've got to be a little careful. You can't just say 1 over x goes to 0 is the same as x goes to 0. Actually, x goes to infinity is the same as 1 over x goes to 0 plus. So this limit is 1. Interesting. So sine of small over same small goes to 1 in the limit. As I look at it, as x goes to infinity, 1 over x goes to 0. So this is small, and they match. So that limit is 1. So that's the rationale there. So I'm getting a lot of mileage out of my basic limit. And I can use that to solve questions like this. That's the same as one of the first limits that I wrote up. In fact, it is the first limit that I wrote up. So there are multiple ways of doing this, but I want you to get into the habit of doing it like this. Screw the x on the bottom. I don't care about that. I just want to look at sine of small. What I want to do, just ignore the bottom. I just want to work on the top. I would wish that I had sine 5x over 5x, because that I understand. They match. So how do I get the 5x there? Well, if I've divided, I have to multiply. And that's the same as the technique for poly over poly, as the polynomial goes to infinity, right? I divided by the leading term, and then I multiplied it again. Well, here it's a different idea, but I mean, it's the different sort of execution, but it's the same idea. I know sine of 5x behaves like 5x as x goes to 0, so I just divide by it and I multiply it. And now I turn my attention to the bottom. It happens to be x. There's nothing to do. I leave it as x. Okay, so now this goes to 1 because it's sine of small over the same small, and the rest of it cancels down to 5. So in this limit, I have 1 times 5, and equals 5. Okay, as I said, that's not the only way you could do it. You can put a 5 here and multiply by a fifth and that, but I want you to do it this way. And the reason I want you to do it this way is so you can solve badass problems like this. Limit as x goes to 0, sine cubed of 2x, cosine of 5x to the 19, all over x tan 5x squared. Yuck. That's pretty horrible. What are we going to do with it? Well, here's what we're going to do. First thing, I'm just going to make one little modification. When you see sine cubed, it's better to just start off, in this case, as writing this as sine 2x all cubed. And I won't make any other changes yet. All right. Now, What's your opinion of sine 2x? What would I like that to be? I want that to be sine 2x over 2x. So this first term, I'm just going to attack the sine 2x. I would love this to be sine 2x over 2x. Problem is, I got to cube it. And I can't just throw in a 2x there. I have to correct by multiplying by 2x all cubed. Okay, so do you agree that that is the sine part? I haven't done anything other than multiply and divide by 2x all cubed. Okay, how about the cosine part? Well, beautiful thing is, cosine of 0 is 1. So cosine of 5, 0 to the 19, is 1 in the limit. So this is actually doing us no harm. There's nothing we have to worry about. See, if we just plug in 0, you get 0 cubed times 1 over 0 times 0. The 1 doesn't hurt us, so I'm not going to do anything to the cosine. I'll just leave it because it is harmless. Okay, now on the bottom, I have an x. I'm not going to touch that. But the tan of 5x squared, I'm going to take this small quantity 5x squared, I'm going to divide by 5x squared, and multiply by 5x squared. It's not 5x all squared, it's 5x squared. Okay, so the result of these little algebraic shenanigans is that this goes to 1, and this goes to 1. And all that's left is just to simplify. In fact, if you simplify it, this is actually 8x cubed. And so you'll get x cubed over x cubed. And basically, this limit, so cancel out the x cubed and change that to a 2 cubed. And then cancel out this x and this x squared. And in the limit, you will get 1 cubed, because sine 2x over 2x is 1 cubed, times 8, times 1, cosine of 0 is 1. And on the bottom, I get 1, it's the ratio of tan small over same small, times 5. And the answer is 8/5. Okay, stare at that for a few seconds. I'm really running out of time. I probably have to postpone the large case till next time. But is there 5 minutes remaining? Is that okay for the video? Okay. Let's look at this limit. We've almost done it. This is one of the other limits that I wrote up earlier. Limit as x goes to infinity, x sine 5 over x. As I said, this is small. This is small. And, of course, as x goes to infinity, that goes to 0. So here's how I handle this. Forget about the x. Just leave it there. It's not doing any harm. I take sine quantity 5 over x. I divide by 5 over x. And I multiply by 5 over x. Right, because it's sine small over small. Well, this goes to 1 as x goes to infinity. Because as x goes to infinity, quantity 5 over x goes to 0. So that goes to 1, and here, x cancels out the x, bless you. So this is 1 times 5, which is 5. Okay, so maybe it would be worth writing out why that goes to 1. I'm not going to do that because I already did it over here. If you would just look back over here, I did this with a 1 over x and a 1 over x. Of course, here I'm just using 5 over x in both places, and I should use a 5 over there. So that's the rationale for that part. All right, so that takes care of, we've really done 3 of the 4 that I asked. The 4th one is just the squeeze principle, and I'm going to consider that next time when I do the large. But in my last 3 minutes, there are 2 other limits I want to look at, which are kind of clever. And they're going to be quite useful. Let's look at this limit. This is a little bit different from what I've looked at before, because if you just plug in, I said cosine 0 is not a problem, right? That's just 1. But here it is a problem, because you're dealing with 1 minus 1, so you actually get a 0 over 0. If you plug in x equals 0, you get 1 minus 1 is 0, and on the bottom you get 0 squared, which is 0. So how are you going to deal with that? Well, there's a trick, and we've seen the trick before, multiplied by a conjugate. So I'm going to take this 1 minus cosine x, and I'm going to multiply by 1 plus cosine x over 1 plus cosine x. Kind of a nasty little trick, because there weren't actually any square roots around, right? Well, in some sense there were. You see, there is a square. The top is 1 minus cosine squared x. The bottom is x squared times 1 plus cosine x. And of course, 1 minus cosine squared of anything is sine squared. I'm going to use that trig identity that I spoke about 2 weeks ago. And let's just siphon off this 1 plus cosine x here. Okay, no problem. So you get 1 minus cosine squared is sine squared. Now, one little thing that seems like it would be nice to do is pull all this inside the square. See, sine squared x over x squared is sine x over x all squared. And then I have this other relatively harmless factor here. That limit goes to 1, sine x over x. This goes to 1 over 1 plus cosine of 0 is just 1. So this is 1 squared times 1 over 1 plus 1, which is equal to 1/2. And that's the value of the limit. Totally not obvious by looking at it. You would look at it, how the hell would you know that this is 1/2? I don't know. I don't think it's obvious at all. I'm not going to finish this example. I'm going to leave it as an exercise. Consider the same thing, but with an x over the bottom. Not an x squared. Well, in this case, if you actually do it, you'll get just an x there. Now we have sine squared x on the top, but only one x to balance it. So we'll split up the sine squared into a sine times a sine, and if you follow the details, I leave it to you as an exercise, but it is actually in the book, and it's in section 7.1.2 of the book. You should get a sine x over x. You'll have an extra sine x, and you'll have a 1 over 1 plus cosine x. You see, you don't have two x's powers on the bottom. You just have sine x over x, another sine x, and if you work out that limit, it's 1 times 0 times 1/2. So the actual limit is 0, and because that's an important one, I'm going to write that this limit, well, equals 0, and put a box around it. Why? Because it equals this, and the details remain to be filled in. So that limit is 0. That will become important next time when we do the derivatives of trig functions. So basically, I have covered all of 5, and I have covered 7.1.1 and 7.1.2. Next week, I'll just mop up the last little sections in there, and then I'm going back to Chapter 6 and finishing 7. So that's the end of the videoing, and stay tuned.